Okay, let's get started. This is second lecture. So before we move on to second lecture, we're going to review and we're going to recap what we learned last week. Okay. Last week we looked at wireless channel. This course is advanced wireless communication. So we're gonna, as I said last week, we're gonna mainly focus on the multi-user communications and the performance analysis of wireless communication systems. But before moving on to any of those details, we need to first review some of the basics and some knowledge on the wireless channels. Okay, so that's why the first 2 weeks we are reviewing the wireless channels. And here's what we learned last week. We start from free space equation, and we say the free space propagation, right? This equation, which we call as a free space equation, basically tells you that what is the relationship between the transmit power and receive power, and what is the function, what does that depends on. So this one, you say that this is P sub r, this is receive power, P sub t transmit power, and G sub t, G sub r, these two are the gains, transmit gain, receive gain, and the gain in transmit and receive, that depends on, let's say, antenna gain, some of the power amplifier, some of the hardware gain. Okay, we include all of those things and put that as gain. Lambda is the wavelength of your carrier frequency. Okay, so you're doing the communication, you must have your own carrier frequency. So wavelength of this lambda is wavelength of that carrier frequency. 4 phi d is the distance between transmitter and receiver. Okay, and L is some other factor. It's a system loss factor. Again, this one includes some other hardware factor. So typically we see the free space equation. A lot of people simply assume that G sub t is to be 0 and L just simply 0, because that really doesn't matter, and this one depends on the hardware. So depends on the hardware, you may have a different coefficient. What is important here is when you have a P sub t as transmit power, the receive power reduces as a d square. Okay, that's what you can see here, and also lambda square, but lambda anyway is a constant. Once you have a carrier frequency, you never change the carrier frequency. So that lambda again can be considered as a constant. D is the distance, but each user have a different distance, right? And each user may move around. So depending on D, P sub r is reduced by square. But this one is only true in free space. Okay? You go out to the space, you took the space shuttle and go out to the space, right? In that kind of situation, this is true. Okay? But in actual environment, of course, it's not a free space, right? We have a building, we have a road, we have ground, right? So there will be some of the blockings, and there are some reflections because of that, right? There are a lot of physical phenomena happening in the actual environment. We learned some of those things, right? Remember? Reflection, diffraction, scattering, those things happen all the time. So because of that, this one is no longer true in the actual environment, but this is going to be the reference point, okay? And we sometimes assume a receive power with the free space, but this is starting point. And as you see here, this G is this one, right? G sub t or G sub r. So gain sometimes consider the antenna gain like this, and you can write it this way. But again, the GT, we consider that as some hardware effect and things like that, so we can ignore that. There's a concept called EIRP, effective isotropic radiated power. What is isotropic? Isotropic basically means that if you have a point source, okay, let's say point antenna. Of course, there's no such antenna in practice, but think about that there's one point source, and this source is radiating the wave, the electromagnetic waves, right? Then this one, since this is a point source, it radiates from every direction, not just azimuthal or horizontal plane, but it goes vertical. Okay, it everywhere. Okay, that means isotropic, right? Isotropic means the everywhere, basically. It it explodes everywhere. Whereas sometimes you see terms like omnidirectional. That basically means that your wave spreads over the horizontal plane. Okay, omnidirectional means that 360 degree on the horizontal or azimuth plane. Okay, that means omnidirection. So anyway, here's the effective isotropic radiated power. So somehow this concept is very similar to our transmit power. But the difference, if you remember, is that the transmit power is the power that I want to transmit. Transmitter has a certain power. I want to transmit this power. But in order to transmit this much power, I use some of the amplifier. I use antenna. And those devices are not ideal, right? They have their own gain. Sometimes antenna will amplify a certain direction, okay? Something like that. So depending on that gain, if you multiply that gain, this was the original power you want to transmit, but there is a certain hardware gain applied to it. You multiply that, and then that's actually what is radiated over the air, right? That's EIRP. So EIRP is what the actual transmit power in the air, not the power that you wanted in the system. That's PT, right? But EIRP is the actual power that is radiated power, okay? That's EIRP. That's a little bit different sometimes. We looked at the three different propagation in wireless communications. First one is what we call as large scale. And you know that that's path loss. Okay? Path loss is large scale. And the middle scale, we know that this is called shadowing. And small scale is fading. Okay? So we need to understand each of them. Each of them affect a different way, and we use each of them for a different purpose. But in wireless communication or in wireless channel, all these things are mixed together. Okay? So let's see one by one. First, the path loss. Path loss, as I said, this is large scale. Okay? So let's see what that means. We have a transmitter here. We have a receiver. And these two are separated by D. Okay, forget about the number of antenna. This can be one antenna, two antenna, doesn't matter. We are not focusing on that part. Okay? Just think about that we transmit something, we receive something, and these two are separated by D. These are distance. Given that, if we use the free space path loss, which we just looked at, okay, this is the one. Then this transmit power, this transmitter uses the power P sub T, right? And we know that the P sub R, which is the received power here, depends on D square. We already know that based on the previous free space equation, right? But we typically use a dB scale for every power, transmit power, receive power, anything like SNR, those things. Anything that is related to the power, we use a dB scale, okay? So you change the P sub R into dBm, and you put the log, 10 log 10. Then you'll see that this equation is now changed to dB scale like this. So this equation is exactly the same, only the unit is different. This is a linear scale, now this is a dB scale. From now on, we use this one, okay? Sometimes you see this equation in the book, but that's a linear scale, right? We want to make it everything as a dB scale. You see that there was a C, okay, just coefficient. This C includes some other factor, like GT, GR, and all the other factors. You put all together because those are anyway constant, okay? So put all these together and put that as a C. Put the log and put it as a C, okay? In that way, we are only focusing on the D. And here you see as a 20 log D because it's a square, okay? You put the 10 log onto this equation, but there's a square, so put this square on the front, that's going to be 20, right? So again, because this is a free space equation. So in free space, this is going to be what's happening. You see the simplified path loss model. So here's what's going. as I said, in free space, the previous equation is true, but in actual environment, this is no longer true. What's happening in actual environment is that this equation has to be changed such that it's no longer d squared. Your power, received power, is now attenuated a little bit higher rate. This one is attenuated by d squared, but in actual environment, it's going to be d to the n. And n, in this case, is higher than 2, right? Could be 3 or could be 4, depending on your environment. Typically, urban environment where you have a lot of buildings, a lot of trees and everything, it's supposed to be higher than rural environment, right? Or free space. So given that, we can rewrite this simply the pathless model in this way. So compared to the previous equation, what you can see is that now we have a 10n log, not 20, because we put the power exponent to n, not 2 anymore, right? And not only that, you see the d0. What is d0? d0 is reference distance. Okay, why do we have reference distance? The thing is that when you do, let's say you want, in this case, right, one of the goals is to measure this power exponent or path loss exponent. This path loss exponent, again, varies depending on the environment. Okay, we'll give you an example on the next slide, but this one changes in the environment, based on the environment. So in order to measure, or in order to find out what is my path loss exponent in my environment, what you need to do is you go out to the field, okay, and then you put some reference point, then you measure the received power at this point, okay? Because that's just reference point, and you have a reference power. Now you go to your position, and then you you measure the received power right there. Then you know what is power here. You know the distance, right? Because that's the reference point is you decided. You decide the reference point and you measure the power. And now again you go to some position. So D, it's under your decision, and you receive the power. So you know the distance of the two locations, this location, that location, and also you know the power here. So based on the relationship between this point and this point, also relationship between the two different powers, you can find out n right here, right? So it says simplified because all the other factor is all like a c sub k. If you look at this equation, this is only a function of n and d0, okay? So why we are doing that? Because we want to find out the power exponent. That's the most important thing in path loss. What is path loss? Path loss is basically how much loss we have over this path. That's path loss, simply speaking, right? So in order to find out how much loss we have under the way, we need to find out n. Okay? Okay, if you have higher n, you have a lot of loss on the way, simply speaking, right? So that's what it is. Okay, so this is a path loss. Here's an example of path loss exponent. I captured this one from a book. And you see that depending on the environment, in free space, as you know, it's 2. But some other environment, sometimes you have a very high value of path loss exponent. Okay? Now, then, we want to ask a simple question. So this path loss model only depends on D. Okay, your received power is reduced or attenuated based on the D. It could be D squared in free space or D to the N. Now then, let's think about that this is transmitter in the middle of some circle, some area, and we have 3 different receivers, and each receiver is separated by distance D. So they are separated exactly the same distance away. Then only based on the path loss, these 3 receivers should receive this exactly the same power, because the received power is only depends on D based on the path loss. But in fact, these three receivers are not receiving the same power, right? So there must be something else. One of them is called shadowing. Okay? What is shadowing? When this transmitter transmits signal, this signal sometimes go directly to the receiver, which we call as a line of sight, right? But there are also reflections from the building, from the ground, from mountain, or there are many reflections, reflections, right? So those reflections, especially the big one, reflections from the big building or big objects, that will affect and make a shadowing. And especially these are random, right? These are random. The reason that this happens is because the transmitter typically use the omnidirectional antenna, right? This transmitter transmit signal into all these direction. So some of the signals go into that direction or some other direction, and that eventually, can reflected and will be delivered to the receiver. So those things will make some shadowing, makes shadowing effect, right? And as you see that this one again is random. So if you consider those shadowing effect, now you can modify the pathless model in this way. So from here to here, that was pathless model we looked at, and we're going to add x sub r. X sub r is a random variable. Okay, this random variable follows a log-normal distribution. Remember that we talked about the log-normal distribution, right? And what was the log-normal? Log-normal distribution is the distribution where you have a Gaussian distribution only when you have a log scale. Okay? If this is a log scale, this is amplitude, by the way. When this amplitude is represented in a log scale, the distribution is going to be Gaussian. But if you show this one as a linear, as what other random variable does, then this is no longer Gaussian. But in this case, right, as I said, all of the power, we always use the dB scale. Okay. Anyway, we start from dB scale because we are talking about all the powers, receive power, transmit power, everything. So anyway, this one, since we write all these things as dB, we can simply consider this one as Gaussian. Okay. So this one is Gaussian right now. Gaussian looks like this, right? So from here to here, this one is going to be a constant when d and d sub 0, all these are constant. Okay, if you go to a fixed location, then from here to here is going to be constant. But x sub r affects a random thing. So now, but this is Gaussian, zero mean Gaussian. So now all the other thing is now work as a mean of the Gaussian. Okay. You know that some constant plus zero mean Gaussian is going to be same as Gaussian with a shifted Gaussian, right? The mean is now shifted. So that's what it is. Okay? That's what you can see. So this picture on the bottom here basically shows you that this is a radio, this is a cell. Or you can say there's a base station here, and this is the area, and this one has a radius, say d, okay? And now if you think about all of the users on the edge, on the circle, along the circle, they do not receive the same power, as I said, because of this shadowing. And at some point, let's make a snapshot. Okay, let's think about only instantaneous time and freeze the time. Okay, just for fun. Then you will see these kind of graph. I'm basically drawing some graph which shows the same power level. So the user here at this instant, user here will receive maybe higher than my reference power, and the guy here will receive the lower power than my line. Okay, so each user in here along the circle will receive the different power. Okay, and the red circle basically shows you the same power. same power line. Okay, all these, if there are user on this red shape, they will have same receive power. Okay, is it clear? But the thing is, this is just instantaneous. Okay, this red shape basically changes. In other words, if you are staying here or anywhere in here, as time goes, your power is now changing. It fluctuates, right? It's all random shape. Okay, but it's random, but it's based on the Gaussian. Right? For example, here, right here, your receive power on average is going to be this much. Okay? This much is going to be your average receive power if you stay here, right? If you stay here, then this is going to be D. This much is D. So you put the D here, and you already know the path loss exponent. So on average, this is your receive power for long-term average. But if you think about instantaneous power, that power is now sometimes high power, sometimes low power. It fluctuates. But that fluctuation, which is random, right? That follows the Gaussian. Okay, so that's what you can find out from shadowing. So remember, we talked about this one, right? This slide. What this slide is trying to show you is this shadowing concept sometimes is used to evaluate the cellular system performance. This is cellular system. This is one cell. We have a base station here, and this is the cell, right? And we have a radius r of the cell. Okay? And again, think about that. The receive power is random. Receive power is random, right? Let's say I'll make one circle with the radius d, and this d is smaller than r, right? And now I'm drawing a circle like this, and I'd like to find out how many users in this red circle, how many users are under service, right? Some of the users are out of service, or I should say outage. What is outage? Power outage, blackout, right? I do not receive. In my receiver or in my cell phone, there's no antenna. Okay, signal is gone. I lost the signal. That's the outage. Some users here, let's say, may be in outage with a certain probability. Some users out here, this guy actually is out of range, in fact, right? But this guy sometimes still gets signal. Okay, why? Because there's a random thing, there's fluctuation. So based on that, what we want to find out is the probability of someone is in outage, called outage probability. How can you find that outage probability? Simply speaking, right? Think about some user who are close, who are nearby of the base station. What is the outage probability for them? Almost zero, right? Almost zero, because they are nearby. But think about some of the users in here on the cell edge. What would be the outage probability for them? Probably a little bit high, right? What we want eventually is to design this kind of cellular system. But the condition is that you should not make your outage probability to be higher than a certain level. You want to make sure that outage probability is less than some level. That level, of course, is under your decision. If you are the guy who are designing the cell, then everything is completely your design, right? But you have to think about the outage probability, because when someone is outage, let's say user here is in outage, let's say in 50% of the time, okay? Then they will be unhappy, right? And they will call up the customer service and complain all that, right? So possibly the outage probability should be maybe less than 10% or 5%, okay? So in order to make sure that one, right? In order to do that, first you have to decide how much power you want to use for base station. If you use the high power, of course I'm drawing a larger circle. I'm drawing this red circle this way because I use only this much power. Okay? You know what I'm saying? You can make a balance, but you can use transmit power as one of the parameter for your system design. Of course, you want to use smaller power, okay? Because large power means probably more money, right? So you want to reduce your transmit power, but if you reduce it too much, then this red circle is shrink like this way. Then all the other users out here will have a higher outage probability. So that's also bad, okay? But if you use the too much power, then this red circle now is going to be big. In that case, maybe you can say that okay, maybe it's okay because everyone is going to be happy, right? Because you transmit higher power than required. But it is in fact not true because there are another cell in here, right? That will affect the interference to others. So it's a tricky issue out there. But typically, when we talk about the outage probability, often we think about only one cell. Forget about the interference to the other cells. Forget about that at this point. That's another issue. Okay? But in this simple diagram, what we are trying to see is we can find out the relationship between the power, transmit power, and outage. This is called outage probability, right? So the relationship between the transmit power, outage probability, and the outage level. Okay, outage probability, and those things, right? And this shadowing can be used to find out the outage probability. So you see that this outage probability, why this is outage probability? Because this is my level, this is my power. If my receive power is less than this power, then I consider that as outage probability, okay? My receive power is too low. I don't understand anything. So that's this threshold. So if your receive power, when you are in the D away, if your receive power is lower than the threshold, that means my signal is too low. So I consider that as outage, right? So what is the probability of such case? This is the probability. You see that this is a Q function, right? Why is a Q function? Because the shadowing follows a Gaussian, right? If you are in the D distance right here, then the signal that you receive fluctuates, right? Based on the Gaussian. So sometimes you have high, even when you are here and you never move, sometimes you receive a good power or high power. Sometimes you receive the low power, right? That you have that fluctuation, but that based on the Gaussian. And you know that Q function, you see here, right? Q function. There's a Q function tells you that the probability that your actual value, in this case we use power, receive power, but the value is higher than this Gaussian, right? So this, you see that this red part, right? So based on the Q function, you can find out the probability of this red part. But in our case, what do we want to do? What we want is we want to find out the probability that receive power is less than gamma. So if this is gamma, then we want to find out this probability on the left side. So you can simply does it like 1 minus Q, or you can reverse the variable. Okay, but anyway, so the message here is that this Q function is used to find the outage probability. In other words, shadowing is used to find out the outage probability. Okay, that's the message. In some of the research paper, you often see the outage probability here and there. Outage probability of this system or some cellular system, and people talk about outage probability. Whenever they talk about outage probability, you just think about the shadowing concept. Okay. And third thing is a small scale fading. This is also very important part. What is small scale fading? Now we look at the path loss, large scale, which depends on the D. Okay, D is very far, the large one, so that's why we call it large scale. But shadowing is middle scale, but small scale is very very local thing. Okay, so let's see why this is happening. So we again have a transmitter, but we have receiver. As you see in the previous picture, there is a shadowing because of this reflection from the big building or from some big mountain or some big objects in the environment. But small scale fading occurs because of some of the scattering around the receiver. So in the receiver, around the receiver, you have a lot of objects also. You have trees, you have small objects around you. Maybe on the street, people are moving around, right? All those things will make scattering. And because of those scattering, what happens is that scattering will make some waveform to break. And you will receiver will receive the wave, electromagnetic wave from all this direction thanks to this scattering. That will eventually cause this small scale fading. Okay, so this picture basically tells you and shows you all these things together. So let's look at these two pictures. Here again, I'm drawing a cell. Well, we have a base station, and we're drawing some area or circle with the radius d. And you see the angle here, theta, right? Going from maybe 0 to all this way to the clockwise. This theta is the x-axis in theta, okay? So if I'm here in the 0 degree, I'm talking about this one. 90 degree, somewhere here, okay? If there's only path loss, then since I'm drawing a same distance circle, right? All these users along the circle should receive the same thing. So receive power should be flat in this diagram if there's only path loss. But as I said, that's not true. You have a shadowing. Okay? So because of shadowing, your signal fluctuates based on the Gaussian variable. Again, this is just a snapshot, instantaneous. Okay? Instantaneous snapshot. So you will see that there's a little bit of fluctuation, like a red one. Red one basically shows a shadowing plus path loss. Okay? Path loss works as the mean, and the shadowing shows some of the Gaussian fluctuation. Okay? Around this path loss. Path loss is mean. Okay? So think about the Gaussian here. Okay? It's a non-zero Gaussian. The mean is path loss. But you see that path loss is like a slow up and down, slow fluctuation. Now let's think about the small scale fading. Small scale fading is like a fading that happens very fast. Sometimes we call it a fast fading. Okay? So this green curve is what you actually see in your receiver. Okay? Okay? Okay. So we call it small scale fading because this fading happens with a very small scale over time and over angle, right? And this shadowing is middle scale because of this. You see this picture basically shows you why we call this one as middle scale, this one small scale, right? Okay, so let's see. We have to talk about very detail about the small scale fading because small scale fading pretty much is very important. If you pick, let's say, the most important thing out of these three characteristics, small scale fading is the one that you have to understand very, very clearly. It will, a lot of people talk about, let's say, relay channel or some other wireless channel or something like that. Most of them talk about the small scale fading. Okay, so let's talk about very detail. Let's look at the details. There are many reasons, okay, why we see the small scale fading. One of them is because of multipath. What is a multipath? As you see, it says a multiple path. You can see in this picture, there's a line of sight sometimes, and there are some reflections and all those things, and scattering and all those things. Those other path, this is one path, maybe the direct path, line of sight. There are many other paths. And because these many other paths are traveling in a longer distance compared to this line of sight, this one or this one will come to the receiver a little bit later. We'll have a little bit of delay because this one basically travels longer way, longer distance, right? Simply speaking, right? So because of that, all these things will be delivered to the receiver with a little bit delay. So look at this picture. This picture is called the power delay profile. Okay, PDP, power delay profile. This power delay profile basically tells you that the first one, most likely, not always, but most likely, the first one is the line of sight path, because that's the shortest path. But you have other path like this. Some here, some noticeable one here, another one here, another one here. These other path must be some other noticeable path which travels longer way. Okay? That will make a multiple path like this. And because there is a multiple path, now we're going to have a small scale fading. Why is that? This is one of the reasons, in fact. Okay? Let's think about one simple thing. Let's say you have some, now you know the Fourier transform, right? We are going to keep talking about the time domain, frequency domain, okay? Vice versa. Let's say in time, this is time domain. We're talking about the delay, so we are still in a time domain. Let's say in time domain you have impulse. If you do a Fourier transform, in frequency domain it's going to be flat, right? Now let's say that if we have not just one but maybe two or some more, then you do the Fourier transform, then what would be the frequency response? The frequency response is long or flat. You will have something like this, some fluctuation in the frequency domain, right? So you can now simply guess that since we have some of the delay or some of the echoes, these are echoes basically, right? You think about that you go on the top of the mountain, okay? And you just say ah in the open air, then you'll hear reflection of your voice, which is echo, right? But you are not only hearing just once, but you're hearing multiple times. Due to the reflections, right? That's what's happening exactly here. You transmit something, but you keep receiving multiple copies, each one with a different delay. That is this power delay profile. This power delay profile basically shows you what would be the delay of each different echoes, okay, and how many significant echoes you might have. Okay, that's the power delay profile. You know the concept of impulse response, right? Going back to your signals and systems undergraduate course, you probably learned the impulse response, right, in signal systems. We call sometimes a channel impulse response because think about that, what we are talking about now is a channel. This middle part, which is channel, let's say this whole thing is a black box, okay? And think about this is simply a system, okay? And we are thinking about the impulse response of this black box. In this case, actually, this box is channel, so we call this channel impulse response. In that case, what you want to find out in order to see the channel's impulse response is that by the definition, you use the impulse for the input to this black box. You should get something at the output. That's impulse response, right? That's a definition of impulse response. We have a black box, right? Let's draw it here. You have a black box here. In this case, in our case, it's channel, but whatever it is, doesn't matter. This is input, this is output. we use impulse in the input, right? Then we will receive something. And this one, the output, when the impulse is used as input, we call that as impulse response, right? In this case, most likely the channel or any other block may have some delay component. In this case, that's what's happening. If there's some memory in the channel, I'm using the different words, but all these things are actually interchangeable. So I'm just keep using it. So think about that, the memory, delay, all of these things are actually same thing, okay? Interchangeable. When you read some research paper, some papers say this is a memoryless channel or memory channel, something like that, right? What does that mean? Memory is hardware, you know, what the hell, what is that? So that means that memory means the delay. Think about that channel in here, you have a delay component, like a Z to Z inverse, right? That's a delay component in block diagram. If you have such a kind of thing, now think about the signals in system, you output will have some input and plus some other input with the delay component, right? You'll have some of the delayed component. This will create another impulse here, right? Think because of this delay component. So when you have a memory in a certain block, in this case especially, that exactly the same as you have a delay component. So sometimes you have a memory channel, delay channel, all these things are the same. So again, coming back to this one, you have an impulse, you have a channel block, you want to find out the impulse response, and most likely the channel we're talking about has a memory in it or delay. So because of that, you have a multiple path, or you have such kind of impulse response, right? Like this one. Okay? So this is impulse you use as an input, and this is the impulse response at the output. Right? So this one, we call that impulse response, and we know that we call that as a power delay profile. You see that this is the time dispersion. You see what that means, right? Time dispersion basically means that you use the impulse, but this one is actually spread it over time. That means time dispersion. There's another factors that affect the small scale fading. Another most significant one is a Doppler shift. What is a Doppler shift? Going back to your high school physics, you learned the Doppler. What was a Doppler? Doppler is something like, let's say you have a transmitter somewhere here, and you have a receiver. Let's say you have a transmitter here. This is transmitter, and you have a receiver somewhere here. If transmitter and receiver both of them do not move, right? Then probably Doppler never happens. Okay? This transmitter transmits certain frequency, and the receivers just keep receiving it. Nothing happens. You just keep receiving the same frequency. But now things is going to be changed when either one is moving. Let's say transmitter is moving. Maybe transmitter can move towards the receiver or move away from the receiver. If that is moving towards the receiver, the frequency that receiver receives is what? Is increasing, right? Frequency basically is increasing. If this transmitter is moving away, then the receiver is receiving lower frequency, right? So from receiver point of view, your frequency changes depending on the movement of the transmitter. Same thing can happen if the receiver is moving. Transmitter stays, but receiver is moving, same thing happens. So because of this movement, okay, so depending on the speed of the mobile, depending on the speed of the surrounding object, that basically means that if transmitter receiver, they just stay, they do not move. But if something around moves, same thing happens. Okay, if something around moves, again the Doppler can happen. Okay, because we have reflections and all those things. Sometimes this one makes the Doppler. So because of these things, we're going to have a Doppler frequency, right? Then let's say we have some of the Doppler frequency. What's wrong about that? When you have a Doppler frequency, right, that means your frequency is now shifted either this way or that way. If the frequency is shifted in time domain, now you have a fluctuation. Okay, you have some change in the frequency domain. Now of course the time domain signal will be affected. Now you have a fluctuation. So you see this picture. This picture shows you the basic concept. Sometimes you have a slow fading, sometimes fast fading because of Doppler. Let's say you have a low Doppler frequency, like you have a very slow movement. Okay. How high Doppler frequency is, that depends on your movement. If you have a fast movement, of course you have a high Doppler. And there's one more thing which affects the Doppler. The carrier frequency or wavelength, right? If you use a higher frequency, right, then with the same movement, do you have a higher Doppler or lower Doppler? Higher Doppler, right? So Doppler frequency is affected by your carrier frequency or wavelength and the speed of movement. Okay, that depends on both of them. Okay, in this case, let's fix the carrier frequency. Okay, let's use just fixed one, but only think about the movement. If you have a slow movement, then you have a low Doppler frequency. Okay, low Doppler frequency means that your fluctuation over time is kind of slow. You have a slow fading. But if you have high speed of movement, or maybe if you use the high frequency, either way you have a high Doppler frequency. In that case, you'll have a fast fading. So fast fading basically means that your now fluctuation, the rate of fading, okay, rate of fading is very high. Okay, you have a very fast fading. That's what we call a frequency dispersion. Why frequency dispersion? Because we now talk about that the frequency or transfer, the function now is changed because of Doppler. Okay, now we are thinking that frequency is now shifted. Let's go back to the time dispersion and look at a little bit more detail. This one basically shows you a power delay profile. The picture that I showed you earlier, this one, power delay profile, this one is very, very simplified version. I just show you this way because this is very simple look, okay? And a lot of people eventually will make the power delay profile as simple as this. But how do you know this power delay profile? Let's say I want to find out the power delay profile of this environment, this room, let's say. How do you find out? You need to measure it, right? Once you measure it, you never see this kind of simple plot, right? You probably get most likely this picture. Okay? You bring your equipment, transmitter, receiver, okay? Measurement equipment. And then install this one and separate by a certain distance and you measure it. You transmit and receiver will keep measuring how a power delay profile looks like. This is most likely what you will see. You will have highest peak on somewhere here, which is most likely the line of sight. And this much would be the delay, propagation delay, okay? And not only this one, that there are many, many reflections from other multipath, but in fact, it's not clean as just a few impulses. You'll have a lot of fluctuations like this. So this is from the measurement, okay? Then how do you simplify it? This is actual measurement, and what you need to do is depending on your condition of your system design, you pretty much pick a significant ones. That's one way. Or there's another technique that this is a time domain plot because we are showing a delay. So from this, you now go to the frequency domain. And then you do some of the signal processing technique in frequency domain, right? And then come back to time domain, such that now the eventual time domain plot is now simplified to this way. you can do some of the techniques in the frequency domain in order to make that. Okay, so for details, if you're interested, we can talk about that later. But what I'm saying here is that this is the power delay profile based on the measurements. You start from the measurements, and from that, based on some of the signal processing technique, you eventually find out the simplified version, which you want to apply to design your system. Okay? But what is the important thing here? Why we want to find out this power delay profile? The reason is that we want to find out these things or these things. So this is the important parameter that we want to get out of these measurements. So let's see. There's a parameter called the RMS delay spread. Let's talk about this one first. Mean excess delay. So here in the power delay profile, you see that from here, which is the first one, to the to this one, to somewhere here. Let's see. Yeah, somewhere. Actually, there are three different parameters. One is that the maximum delay, okay, maximum delay spread, which means that you start from the first one, and you find out which one is the last delay component, and then find out the delay. That's going to be the maximum delay. But in this case, as I said, this is based on the measurement. So what's happening is this is going to be the first line of sight component. There's some reflections, and it's keep reducing because now as time goes, your reflection is going to be reduced, and eventually it goes into a certain way like this. All these things you can consider as a noise. So it's completely up to you. Where is the noise? And what is the threshold that we consider as a noise? In this picture, you see that this line, horizontal line, in -20, this one is the noise line. Okay, this is a noise level, what noise level that they consider. Depending on the situation for you, maybe you can consider that this is not the actual noise level. Maybe you can increase this one as here. And I would consider that this one is my noise level. You can do that. It's up to you, okay? But in this case, they consider that this one as a noise level. So in that case, you cut it here, and all the other component in below the noise, we just remove it because we said that this is a noise level. All the power lower than that is absolutely noise. So let's ignore all this, okay? Let's ignore all this because that's noise. So the last significant component or delay component would be this one, okay, in the power delay profile. So now the maximum delay would be from here to here. That's going to be the maximum delay. That's one parameter. Another parameter is the mean excess delay. That means the mean of the delay. We have this one, probably delay is 0. This component, the delay is going to be this much. All the delay is reference to the first one, okay? Because the first one is a line of sight. We are not talking about the propagation delay. This one is some other delay. We don't care about propagation delay in this case. Propagation is related to the path loss and some other things. In this case, we are talking about small scale fading. So all the delay we are talking about is compared to the first one, the line of sight, right? And so this much is delay. For this component, delay component or multipath, we have this much delay. So each component will have a different delay. So we do the mean. We take the average of that. That's the mean excess delay. So in this case, this is going to be the maximum delay. So the mean delay is something around here, right? Maybe. And you see that here is RMS delay spread. Okay? So RMS delay spread is calculated this way. This way. Okay? Second moment minus the average square, and you put the whole thing as a root square. That's the RMS delay spread. This is probably the most important thing. The probably most important parameter that you want to find out from this power delay profile. And this is possibly the reason why you are doing this measurement. Then you want to ask, why do we need this? This is the goal of this power delay profile, and why do we need that? Okay? That's probably that's probably the question, right? We want to find out this power the delay spread, then why do you want to get that? So before I answer that question, let's see some of the examples. This picture again is from one of the books, okay? And this table basically shows you some of the examples based on actual experiments some time back. Okay, some of the urban environment, suburban, indoor. Depending on the environment, and also they use these much frequency, they use completely different delay spread. Now you can make your guess. Let's say you go out to the field, go out to a certain urban environment, okay, and then put some transmitter and put your receiver somewhere, and let's measure the delay spread. How much delay spread do you think you get? Compared to the indoor environment like this, your delay spread is going to be very large, right? Because that's outdoor. Think about all the reflections. Your reflection is from the building. Anyway, those reflected path will have a very large distance, okay, large traveling distance. That will make a large delay spread, right? So as you see here, typically the delay spread, the range of delay spread, of course, is pretty big, but this is somehow average. It's like this much. You see that it's a millisecond level. Sometimes the microsecond level. So it's like a 10 to 25 microsecond. It's like 1.3 microsecond. It's a 3.5 microsecond. It's a microsecond level. But think about the indoor. You see that this is nanosecond, like 10, 50, 200 nanosecond. Why? Because indoor is a small environment, right? Reflections is like immediate, almost immediate, right? So apparently, in indoor environment, you will have very short delay spread compared to urban. So this urban is measured in New York City or some San Francisco, like big city, right? This indoor measurement, they did that in some office building. And I don't know what is the material of that. In fact, the material is also important, right? When you do indoor measurements, say your walls and ceiling, all of them are metal, you probably get a different result, right? If all those things are like wood, get a different result. So I don't know much about that, but this book, in fact, has also another table that shows you some of those things depending on the material. Of course, they thought about that. They have done those experiments also, right? But this one simply shows you the delay spread values, some examples of delay spreads. Okay, now you want to remember that in outdoor environment, like a cellular system and things like that, they work based on the delay spread of microseconds, tens of microseconds. But in indoor system, typically the delay spreads is like tens of or hundreds of nanoseconds. Okay, that's something that you want to remember. Here's the reason why we think that delay spread is important. Now, again, as we looked at, this is somehow a delay spread. This is a maximum delay spread. You can think about the average of them or RMS. Either way, all these things is delay. We are talking about the time domain, right? This delay spread. But when you have some of the delay like this, or delay component, again, as we said, when you do the Fourier transform, in frequency domain, you will have a fluctuation. If you have a more delay, possibly you have more fluctuations. It's no longer flat. So how does that affect our system? You see that there's a concept called the coherence bandwidth. Let's see what it is. This is frequency domain, and what coherence bandwidth basically tells you is that in this frequency domain, how much of the bandwidth we can consider as a flat. That's a coherence bandwidth. Okay? So in this case, right, since we have this much fluctuation, maybe I can consider this one as almost flat. Of course, it's not exactly flat, but I want to consider this much as a flat, almost. Okay? And this much, I think is flat. But if you have more multipath or large delay, then I think most likely your fluctuation is like this, right? In this case, your coherence bandwidth is going to be very, very narrow. So the large delay spread basically means that you have a short coherence bandwidth. In another way, right? And the other way, let's say in extreme case, let's go back to ideal case where you have only one impulse, one impulse in the impulse response. If you have this kind of impulse response, okay, you transmit impulse, you receive impulse. That's perfect. Very, very ideal case. In that case, in frequency domain, you have a flat transfer function. In this case, coherence bandwidth is infinite. Of course, this is very ideal, but okay, this is the extreme case. So now, what you want to remember is you have we talked about delay spread, right? RMS delay spread. If you have a high or large delay spread, that means you have a short coherence bandwidth. So it's inversely proportional, like this. Whether you use 1 over 5 as a coefficient or 1 over 50 as a coefficient, that depends on the people. Okay, some people say, okay, your coherence bandwidth is proportional to 1 over 50. What is this one? Sigma? Sigma, right? Well, 50 is sigma. Sigma tau, this is a delay spread. Okay? So anyway, regardless of any equation, your coherence bandwidth is inversely proportional to the delay spread. But sometimes some people use 1 over 50 as a coefficient. Some others use 1 over 5. Doesn't matter. What is important here is your coherence bandwidth is inversely proportional to your delay spread, as we just looked at. Okay? So that's an important thing. Right? Okay, then simply speaking, right? Large delay spread like this give us more headache. Okay? We'll see why later, but large delay spread give us more headache because of many reasons. But one of the reasons is, again, this large delay spread will make a very short coherence bandwidth. Okay, you have a more fluctuation in the frequency domain, which is a problem. Okay, but this problem is something like you cannot change it. Okay, what we are talking about here, right, is a wireless channel. You cannot change wireless channel. Wireless channel happens, and all these things, right? All these physical thing happens on the channel. Okay, delay spread. Whether you want or not, this won't happen. In this environment, this will happen anyway. Okay, you don't want this, but this will happen. Okay, you have to go with it. So what you have to do is you have to understand these things, which is a physical thing, physical phenomenon, right? Physical thing happen in the environment, and then based on the understanding, you will want to use some of the technique in order to remove it or in order to reduce it, right? That's why we want to understand what's happening over there. So this is one of those things. So official definition is the range of frequencies over which the channel can be considered flat. That's the official definition of coherence bandwidth. As I said, that's inversely proportional to delay. Now let's think about Doppler. As we looked at, we have a Doppler frequency, right? Doppler frequency is the frequency dispersion. You have your frequency is now shifted because of the movement. Okay? Once you have such thing happen, let's say you have a Doppler. Now, what that means is that your let's say this is your bandwidth, and because of Doppler, your spectrum now moves, okay, or moves the other way. So if something happens in the frequency domain like this, now that of course affects the time domain, okay, in time domain. How does it affect? Is that simply speaking, as we looked at, if you have a slow, if you have a low Doppler, frequency, you have a slow fluctuation, right? You have a high Doppler, you have a fast fluctuation. So why is it important? Again, Doppler is something you have to go with it, right? So this is going to be what's happening, okay? Whether you like it or not. So why is it important to understand these things? Let's say you have a transmitter here, you have a receiver here. You want to do a communication, okay? But what you want is you want to communicate with no error, okay? Of course, that's what you want, right? Or small error. Now think about that. Now the channel is channel fading is fluctuates this way. So this kind of fading is now breaking everything, break your packets, okay? Your signal, your transmit signal. Because sometimes the channel will have a very low power. So if your packet, let's say, looks like this, right? And if your packet, unfortunately, go through this region, then your packet go through a very low gain in the channel. So the receiver most likely will receive a very, very low power. So the receiver cannot recover your packet, okay? Simply speaking. So we have to understand this Doppler and this fluctuation because here, due to this fading, we want to understand how much of the time duration we can consider as a flat. That's the concept of coherence time. Same as coherence bandwidth, right? We talked about coherence bandwidth. But there's also concept called the coherence time. So that basically means that this is time domain. And we want to understand how much of the time duration we can consider as a flat. If that was a low Doppler case, this coherence time probably is large. But in the high Doppler case, the coherence time is going to be very small, right? So again, the Doppler is inversely proportional to this coherence time. Low Doppler, high coherence time. High Doppler, low coherence time. But again, going to my previous question, why is it important to understand the coherence time? Because that coherence time gives you an idea how much my packet should be. If your packet is much larger than coherence time, then it is no guaranteed. It is not guaranteed that your packet is safely delivered. You see what I'm saying? Yeah. That's one of the parameters that you want to consider when you make a packet. So that's one of the reasons. I'm saying packet, but in fact that's a symbol. Okay, symbol. I'm just giving you a concept. Okay, so let's look at the equation. So as I said, that this coherence time, T sub c, is inversely proportional to the Doppler frequency. So it's inverse. Again, some people use just 1 over FM. Some other people use 1 over 16 phi or this kind of complex coefficient. But either way, doesn't matter. Important thing is your coherence time is inversely proportional to a Doppler frequency. That's the important thing you want to remember. Okay, actual coefficient, you can look up the book. Okay, some people use this one, other people use this one. So you can use one of these. So far, what we talked about is the First, the time dispersion of the channel. And second, the frequency dispersion of the channel. So all these things is what we call a small scale fading. Okay? Small scale fading. So we have delay spread because of the multipath. And when you have a multipath and when you have a delay spread, that will make some of the fluctuation in the frequency domain. So we need to think about coherence bandwidth. When we have a Doppler frequency because of movement, okay? We have a movement, so we have a Doppler spread. Whether you have a fast or whether you have a high Doppler or a low Doppler, you might have some large coherence time or small coherence time. And also you see the fast and slow fading. We'll look at what this means, flat and frequency selective in the next slides. Do you have any questions so far? It is important to understand these things. Time dispersion, frequency dispersion, and the delay spread, coherence bandwidth, coherence time, Doppler shift. This is very, very basic thing. You have to understand it very clearly. This picture basically shows you or illustrate what is actually happening when you have a Doppler, when you have a multipath. Say that this is a multipath or power delay profile, right? And now let's say this transmitter transmits these packets. At the transmitter, this is my packet. The actual symbol, yeah, the whole thing is a packet, but my symbol looks like this. This is a symbol duration. What is a symbol, by the way?
Number of bits.
Could be number of bits, but in fact, when you talk about bit, you're talking about the information here, right? Your original information is bits, right? Since we are talking about the channel, we no longer talk about bits, okay? Yeah, I understand what you're saying. It's conceptually it's correct. But when we talk about the bits, that's like something here and something here, right? After you do all this processing, you eventually recover the bits. And originally, you want to start to transmit bits. But when you go through the channel, you are not transmitting bit, it is, right? You are converting the bit into symbol.
It's like symbols, voltage levels.
Symbol what?
Voltage levels.
Voltage. It could be voltage levels. It could be phase, or it could be anything else, right? But symbol is different from bit. Eventually, you're going to change the bits to symbol. The easy way to do is modulation, right? Yeah. So we are going to use a symbol because we are talking about channel, right? When you talk about the digital communication system, like this part or this part, people talk about bits, symbol together, but we no longer talk about bits here because we're talking about the channel. What is flying or flowing over the air, that's all symbol, okay? So let's say this is one symbol. It could have been bits originally, right? Maybe if you use QPSK, maybe there are 2 bits which are converted into one QPSK symbol. But anyway, this is symbol. So we have a symbol here. It looks big, but looks one symbol. There's another symbol here. Okay, this transmitter simply transmit all the symbol one after another. Okay, some signal goes this way, that way, this way. You see the color code, right? The black one, red one, green one, and you see that the black one probably has the largest traveling path, so there will be this much delay. You see the red one here, right? Red one probably travels shortest path, so it probably comes first, something like that, right? So this is again very simple plot just to help you to understand, right? So given this environment, now we transmit these 2 symbols, then receiver first of all receive these red symbols throughout this path. Okay? But there is another path, so you will receive green one and another copy, like black one, right? But each one reaches the receiver with a little bit of delay. Okay? Red one comes first because as you see here, red one is pretty much the shortest path. Red one arrives here at certain time, and a little bit later delay, which is this delay. After this delay, the green one arrives here. With a little bit more delay, this much delay, now the black one arrives. So what is actually happening in the receiver is the addition of all these things. That's what you receive, right? You are basically receiving the addition of the whole thing. Then what is happening is, look at this one. You have one symbol, original symbol, the first symbol here, and the part of the first symbol is now mixed or added with the second symbol. And because of this multipath, now here, some more part of the first symbol is now added with the second symbol, right? So these things is what we call as inter-symbol interference, because one symbol is now interfering the next symbol. So inter-symbol interference is happening, right? Because it's a multipath, this will happen, of course. Okay, but here in this kind of scenario, inter-symbol interference is very bad, of course, right? But this happens, but still it's okay. Why? Why is it okay? In this scenario, it's okay. Because in the receiver, you receive this whole thing, and eventually you should do sampling, okay? When you do sampling, most likely you do a sampling somewhere in the middle. This is one symbol, you do some sampling here. You take the sample out of this point, or maybe somewhere in this point. But since you pick some sampling right here, and also somewhere right here, to recover the first symbol, second symbol, this inter-symbol interference is pretty tiny, okay? So when I do sampling, I can recover the first symbol, second symbol with no problem. So this inter-symbol interference does not affect your performance, okay? Because the delay is actually pretty short. Pretty short is a little bit vague term, but more exactly, this delay spread is shorter than my symbol duration. So if the symbol duration is pretty large, in this case, this symbol duration is pretty large, right? But compared to that, this delay spread is pretty short. So this kind of small inter-symbol interference does not affect much. Okay? This kind of condition is called the flat fading. Okay? So here, it says that no inter-symbol interference with the proper sampling. When you do the sampling properly, the inter-symbol interference does not affect you. Okay? So you're fine. So that basically means that since when you do sampling, you can recover the original symbol perfectly, you don't have to worry about delay. There are actually delay spread, but for you, you don't see anything. Okay? You don't care because I can recover perfectly anyway. Okay? That means flat fading. It's a flat. What is flat? Flat fading means that I have flat fading in frequency domain. But in order to make it flat in the frequency domain, your time domain should have impulse, right? But this one is not impulse, but I can consider that as an impulse. No problem, because anyway, I recover perfectly. So I would consider that as a flat. It's almost flat, right? For me, from my point of view, it's flat anyway, right? It's a flat fading. Let's think about another condition where your symbol duration is pretty short. Okay? In this case, the transmitter transmitting multiple symbols as we did before, but this symbol duration is pretty small. Compared to that, my delay spread is pretty large actually. I have a 3 different paths, but I have this much of delay. Now think about this condition. Let's do the same thing. This is what you transmit, symbol by symbol, and over this red path, you receive this one. And a little bit later delay, this much delay, you will receive the same copy over the green path. A little bit later, again, you receive the same copy over the black path. So these are all mixed together. Now let's do the sampling. You do a sampling somewhere here in the middle to recover the first symbol, second symbol, third symbol, fourth symbol. Now we have a problem because look at this one. This one, the first copy is now, the first symbol is now added with the second one, and even third one. So when you sample here, in order to recover the second symbol, you cannot recover second symbol perfectly, because now the part of the first symbol is mixed together. Part of even second let's look at this here, right? Let's do sampling on the third symbol. Let's say I do the sampling here in order to recover the third symbol. Part of the first copy is first symbol is added together. Part of the second symbol is still there, right? So I cannot recover my third symbol perfectly, because the intersymbol interference still affect my receiver, right? So in this case, just the sampling, you cannot recover. So you have to do something, okay? You have to go through a certain technique, very expensive technique and very, say, difficult thing to remove all these things, okay? Undoing these things is very expensive. What is the technique to do that? Equalizer, yeah. Equalizer is the one we need to use in order to avoid this. Okay, you have to do equalizer. Equalization is pretty expensive, but you need to do that for this case. So this condition is what we call as intersymbol. Again, the intersymbol interference is this much. This is what we call as a frequency selective fading. Okay, frequency selective. So we talked about flat fading earlier in the previous slide. And this slide shows you the frequency selective fading. We have two different fading. Frequency selective fading, which is this one, is much more headache, right? Because we need equalizer. In the previous flat fading, you still need the equalizer, but that equalizer is nothing. You just change the gain. Since over there you have some of the fading, so you just adjust the gain. That's it. The equalizer is very simple. It's almost nothing. But this one, it's not that complex. It's not that simple. You need to have a very complex equalizer. So, but this one is most likely the scenario for us. Why? Because it goes back to this one. This is a flat fading, which is simple case. But there's a problem here. The problem is that this is only true only when you have a large symbol. Large symbol means very low rate, low data rate. We are not interested in low data rate, right? We are mostly interested in high data rate system. Okay? So in high data rate system, most likely this will happen. So we have to deal with this kind of scenario. One way to do it is, as I said, equalizer. Okay? That's why if you go back like 20 years ago, maybe even 10 years ago also, right? Or 20 years ago, a lot of research scientists and engineers, they worked on the equalizers. So equalizers is one of the hottest topic at that time, because everyone knows these things, and everyone believes that equalizer is the one that you have to use in order to avoid these things. So that was pretty much the hottest topic. Okay? Now there's another technique to avoid that, which we'll talk about much later. But simply speaking, you can use OFDM, okay, to avoid that. Okay, you heard about OFDM, right? OFDM is not the technique to remove this. In fact, that's some other technique. That's basically transmission technology. But when you use OFDM, these problem is gone, basically, in nature. But anyway, we'll talk about that much later. But what is important in this class is to understand the flat fading and frequency selective fading, and when such thing happens. So let's look at the types of small scale fading. Okay? We looked at the flat fading and frequency selective fading just now. And what was the case of flat fading? Bandwidth of the signal is the bandwidth of the channel. In other words, delay spread is less than symbol period. Delay spread is less than symbol period. That was a flat fading, right? Let's go back to this. Delay spread is less than symbol duration. In other words, symbol duration is much larger than delay spread. That's the case of flat fading. Okay, that's the case of flat fading. If your symbol period is smaller than delay spread, or your delay spread is very large compared to your symbol duration, right? Or delay spread is very large compared to your symbol duration, or you have a high sampling frequency, that is most likely the frequency selective fading. This is very hard to deal with. Okay? So you need to understand clearly about flat fading and frequency selective fading. There are another category called the fast fading and slow fading. Slow fading, that's the case of low Doppler shift or low Doppler frequency. That's also the fast fading is the case of high Doppler frequency or high Doppler spread. Okay? In this case, you use a high Doppler spread, so you have a fast fading. Therefore, your coherence time is much small. You have a fast fading, so you have a very small coherence time. Okay? Think about now you have a small coherence time, like this one. This is a case of high Doppler. You have a very small coherence time. Do you think you have to use a small symbol duration or large symbol duration? In this case, you definitely want to use small symbol duration because coherence time is small, right? If you use large symbol duration, again, some part go through the deep fading, right, and things like that. So the safety or integrity of your symbol is not guaranteed. Your symbol is now gone through the deep fading, so the information is lost. Okay? When you have the low Doppler frequency, you have a large coherence time, so your symbol can be as large as that much. Of course, if you want, you can make it smaller, no problem. But you don't want to make symbol to be larger than coherence time. So the coherence time basically gives you a guidance. Okay? Give you a guidance about this possible symbol duration or symbol period. Okay? This is another picture that again summarizes the where the frequency selective fading and slow fading fits in. So here you see the flat slow fading, flat fast fading, frequency selective slow, frequency selective fast. So as you see here, the fast fading, frequency selective fading, that these two depends on the time, depends on the delay spread. If you have, let's say you have fixed the symbol period, okay, your symbol period is this much. Now let's think about two different conditions. One, you have a very small delay spread. In that case, it's going to be flat fading. Okay, I have a fixed symbol duration, but in my environment, I have a very small delay spread. So of course, the flat fading, it becomes a flat fading. But given the symbol duration, in a certain environment, if my delay spread is very large, that's going to be frequency selective fading. So whether it's flat fading or frequency selective fading, that depends on your delay spread. This one, right? Whether you have a fast fading or slow fading, that depends on Doppler. Okay? You see what I'm saying? So whether it's a fast or slow, that depends on the Doppler frequency. Whether you have a flat fading, frequency selective fading, that depends on the Doppler. That depends on the delay spread. So this is a time domain. No, this is not a domain. No, this is a symbol period or transmitting symbol. This one is a symbol period, transmitted symbol period. You can see that this area is slow fading. This area is fast fading, and this flat, this frequency selective. You can see the same way using the frequency. Okay, so think about that one. If we have a very let's see. So this is a transmit symbol period, and when you have a large symbol period like this one, then most likely you will have this one actually. This one is a coherence time. Yeah, right. So this is a coherence time, right? Remember that what was the coherence time? This one was coherence time. So if your symbol, this symbol is larger than coherence time, which means somewhere here, this is a coherence time, but you want to make symbol period to be larger than coherence time, that means you go through the fast fading. Okay? Because within your symbol, you have a fading inside, so that means fast fading. Okay? Inversely, you have a slow fading in here because you have this much of coherence time, but your symbol is very small. So anyway, within that symbol, you have a flat, you have slow fading. So that's what it is. Same way, this area you have a flat, and this is frequency selective. Okay. Now I want to talk about a little bit about these things. You keep hearing and you keep reading this Rayleigh fading distribution or Rayleigh fading channels. Okay, somewhere in the research paper. Okay, pretty much every paper about wireless communication, they talk about Rayleigh fading or some other fading channel. So now we want to understand what it is. Okay, so here's what it is. First of all, Rayleigh fading is a mathematical distribution. This is just a fading. It's not a. It's a some of the distribution, random distribution. So it has a PDF like this one. If you Google it, you Google the Rayleigh, then you will see these things, right? It looks like this way. You see the Gaussian distribution, right? Gaussian distribution depends on two parameters, mean, variable. Okay, once you know the mean and variable, you can exactly characterize the Gaussian distribution. Rayleigh distribution is characterized by only one parameter, sigma here. Okay, once you know the sigma here, you can exactly characterize this PDF. So depending on the sigma, you can draw the PDF. Okay, sigma equal to 1, sigma equal to 2, you have a different picture. Okay, different PDF. But this one is what the PDF look like for Rayleigh. And of course, when you have a PDF, of course you do a CDF, right? So this one is a CDF. You do the integral of that like this way, right? Then you get this CDF of Rayleigh fading, Rayleigh distribution, not fading, Rayleigh distribution. Then depending on sigma, again, if you draw it, then you get this picture. Okay? So this is just mathematics. So far, nothing to do with our wireless communications. This is just mathematics. Okay? Rayleigh distribution. Now we want to understand, this is just mathematics, Rayleigh distribution, and what's the relationship between this mathematical equation with our wireless channel? Okay? That's what you want to understand. So before that, we have to talk about these things. This is what is actually happening in the physics. So let's say this is a simplified picture, but I'm basically illustrating a scenario where you have a transmitter somewhere here, you have a receiver, and there are a lot of objects around the receiver. And because of the scattering there, you will receive the electromagnetic waves all around the angle. Okay? You get the electromagnetic waves or signals from all different directions with a different angle, different power, different phase. From the mathematical standpoint, the received power is the addition of all these random variables. Okay? Each one of these. This wave follows x1t. This one is, let's say, is x2t. There are millions of them. Thousands of millions of them, right? That comes all together with a different phase, different angle, different magnitude. So let's say that this one, the x1, is like a1t plus jb1t. This is complex value, right? We consider this one because we have a phase here, right? And this x1t is a sinusoidal function basically. So we consider this way, x2t same way, we consider this way, and all the other things we write it in the same way. Okay? And this, there's something error here. This is not supposed to be here. But xt, which is the received symbol, is now the addition of all of them. Now let's think about it. Each one of these is a random variable. Okay? And you are going to add all this random variable in order to make a new random variable. Then, based on certain theorem that we know, right, we can guess what would be the statistics of that. We know that, right? There's a theorem called the central limit theorem. Okay? Based on central limit theorem, we know that when you add all these random variables, this one approaches to Gaussian. That's the central limit theorem, right? It doesn't matter what is the actual distribution for each random variable. Doesn't matter. Okay, when you add millions of them, the result, when you add all these things, this new random variable basically follows the Gaussian. Okay, that's the central limit theorem. So based on that, we know that there's x of t now follows a Gaussian. Okay, so x of t. Okay, so something is wrong in the old PowerPoint slide, but here's the message. So when you have this environment, now the x of t, which is the addition of all these random variable, this one now follows the Gaussian. So let's say this x of t, let's say we want to write as x r plus jxi. Let's write it this way. Okay? And we know that this one follows a Gaussian. So this is a complex Gaussian. Okay? Complex Gaussian. We think about the complex value and we are thinking about the Gaussian for each of them. Okay? Given that what we are interested in is to find out the amplitude of the received signal. How can you find out the amplitude? Here the amplitude is going to be xr squared plus xi squared. That's the amplitude. Okay? Now it becomes a mathematical problem. This is a Gaussian random variable. There's another Gaussian random variable. There are two independent the Gaussian random variables. And now you do the square for each of them and you add it and put the root square. That's going to be new random variable. What is going to be the distribution of that? Okay? That is the mathematical problem. Okay? Mathematical problem. Based on the physics, right? We're talking about physics now. And we basically convert the physics problem to the mathematical problem. And you do derivation like this, and you solve that mathematical problem, then we eventually get the Rayleigh distribution. So x is the amplitude, this is a Rayleigh distribution. And then even further, we can go even one more step. Now x follows a Rayleigh distribution. Now I want to understand y, new random variable, which is x squared. Okay? X follows a Rayleigh distribution. Now I want to consider another random variable, which is x squared. Then what is this random variable? This one is exponential. Okay? Some of you who took my class in the previous semester, you understand this one, right? We already talked about all these things before. Okay? So this one now follows exponential. All these things is a simple mathematical problem. You can do that. Okay? You can solve this by hand. Okay? Yeah. So y now follows exponential. I said this is what? This is amplitude. Okay? X is amplitude. When you do the amplitude square, what is this one? Now it's a power. Okay? You do the amplitude square, now we are talking about the power. So in other words, in Rayleigh fading channel environment, your receive amplitude follows a Rayleigh. And if you think about the power, receive power, that follows exponential. Okay? So that's why whenever you see the research paper, the paper says the performance analysis of some system in the Rayleigh channel environment, but they sometimes show exponential distribution in the paper. They said Rayleigh fading, but they use exponential distribution. Why? Because they are thinking about the power. And most likely a lot of papers they use SNR as one of the metrics, right? They always use SNR because performance most likely depends on the SNR. You have high SNR, good performance, simply speaking, right? So everyone uses SNR. SNR is the power, right? Signal power divided by noise power. Signal to noise ratio, right? But each one is power. Signal power, noise power. So definitely exponential, okay? So in this case, that's one thing that a lot of people confuse. A lot of people are confused. Whenever we are talking about power, you have to use exponential distribution based on this mathematics, okay? Distribution. Something is very wrong here, but here's the thing. There's another fading channel called the Rayleigh fading. Okay, Rayleigh. Okay, we talked about Rayleigh, but now we are talking about Rayleigh fading. Rayleigh fading has some distribution which is not shown here. I'll update this PowerPoint slide and re-upload in the. Oh, is it shown okay? Yeah, okay. In your lecture note, it's shown okay. I think that there's some problem in the PowerPoint version, so bear with me. So this one has some equation. Your lecture note has an equation, right? This Rayleigh distribution depends on the two parameters, this and this one. Okay, here's a sigma and v. Okay, and you also see a CDF of this. But we are interested in more about understanding behind this Rayleigh distribution. So let's go to the physics again. Okay, we have a transmitter. Again, we have a receiver. Same way as before. But what is different compared to the Rayleigh case is that now in this case, let's say that we have some of the line of sight. Earlier, we are only considering a scattered environment. So there's no line of sight. In fact, that's mostly the case for us. Let's say you are using cell phone in this room. There's no line of sight. In fact, I don't know. Where's my base station? I never see it, right? So line of sight is not guaranteed. That's Rayleigh, pretty much. But in this case, in Rayleigh environment, your line of sight is guaranteed, okay? Suppose that's the case. So you have a line of sight, and all the other waves are coming from some environment based on scattering, same way as Rayleigh. In that case, going to mathematics, now we are again think about this is x1t, x2t, all the others, right? As before. So x1t, x2t, blah, 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 right? And now, same way, we're going to add all these together to make another random variable. But since there's a one line of sight path, let's say there's one line of sight path, and suppose x1t is a line of sight. In that case, earlier, each one of these was zero mean Gaussian, okay? But now, this line of sight component, line of sight random variable is not zero mean Gaussian. It is a Gaussian with a certain mean. Why it has a mean? Because it has a direct line of sight. It gives us some strong power compared to others. Compared to others, this one is much stronger because you have line of sight. So when you add it all together, now this ZT is no longer a zero mean Gaussian. Again, you use a central limit theorem. Okay, so you do the central limit theorem. Eventually, the result is going to be Gaussian. But earlier in the Rayleigh case, it was a zero mean, but now it's not zero mean because of this strong path. Okay, this strong path is now work as the mean. So now this x of t is going to be the Gaussian with a certain mean. It's a non-zero Gaussian, non-zero mean Gaussian. Okay? Then what you want to do is you want to calculate this one again. Okay? But what is different compared to the earlier case was that this xrt square, x of r, x of I, these two are non-zero mean Gaussian. Okay? That's the only difference. These two are non-zero mean Gaussian because of this line of sight. Then now let's find out x. Again, this is a mathematical problem. So let's find out what would be the PDF of this new random variable. But these two are non-zero Gaussian. Now x follows a Rayleigh distribution. In fact, solving this one is very complex. Earlier case, zero mean Gaussian, and to find out the Rayleigh distribution, that is pretty simple. Some of you remember that, right? I used this one as one of the problem in the midterm. Remember that? I used this one as a midterm. Okay? I just give you a warning. I might do that again. Okay? But that was a Rayleigh case. It's as simple as that. You can solve it right away, even in the midterm, in the Rayleigh case. But in Rayleigh case, it's very difficult. Only difference is that this is a non-zero mean Gaussian, but it's very complex. So we'll just refer to the result. This one follows a Rayleigh distribution. Okay? So difference compared to the Rayleigh is that in Rayleigh fading distribution, think about the environment, line of sight path is there. That's the only difference. All the other slides, the remaining slides are talking about the simulation of Rayleigh fading channel. Some of you remember that we've done this in one of the projects in the earlier lecture, right? Earlier course. Some of you took the wireless communication, and I asked you guys to do some course project, which is doing some simulation of these things in MATLAB, right? But this semester I'm not going to do that. But this basically a couple of the other slides, that shows you how to do that. Okay, all the details are in the book. So in order to do the simulation, by the way, why do you want to do simulation of channel, wireless channel? Because you want to evaluate the performance of your system, right? Let's say you develop or you propose your own system, anything, OFDM or any other system, right, of your own. Or some of you may be interested in receiver side, so you want to evaluate the performance of your receiver. How would you do that? You want to do simulation, maybe in MATLAB or somewhere, some other platform, right? So you have to bring your own transmitter, maybe your receiver, right? You have to have a channel, okay? So anyway, when you want to evaluate the performance in simulation, you need a channel, okay? So you should be able to do this, okay? The very basic and very important. In order to simulate the Rayleigh fading channel, there are two different ways. Some people use Jake's model to develop the simulator. Some other people use Clark and Gann's model. So let's review two different models. First model, Jake's model, is like this. This is a simple block diagram of Jake's model. And the details about the Jake's model is in this book. So he wrote a book sometime back, like about 18 years ago, in 1994. And this book has every single details about this model. But simply speaking, right, this model is also called a sum of sinusoids model, which means that this is the output. This is the output. And we want to get some of the Rayleigh fading channel right here. Okay? But in order to make that in the simulator, you first generate some of the sinusoids, like some sine, cosine, each one has a different frequency, as you see here, right? And then you generate multiple of them. The more, the better. And then you are adding here in sine. You collect all this cosine and you sine it, right? And then you do some of the multiplication like this one by your frequency, and you add it together. Okay, that's how you can make the Rayleigh channel. And the idea behind this is basically this one, right? Look at this one. This one is the sum of all the sinusoids, basically. Think about the physics, right? Again, going to physics, you have a receiver, you get all of the electromagnetic waves from all this direction. Each one of these electromagnetic waves is sinusoids. You get sinusoids here, another sinusoid from another direction. Each one has a different angle, different phase. So given that you are doing similar thing, make a lot of sinusoids, okay? Since we are talking about the complex value, x, the real imaginary, right? Complex value, you make this way, make it real, make this is real, and this is imaginary, and you're adding together, and that's gonna be your fading channel, okay? So that's a Jake model. One of the problems in Jake's model is that there's no randomness. In fact, the channel is random, very random, right? But here, there's no random because everything is deterministic, right? You fixed everything, basically, okay? So when you do a simulation like this, you can actually specify the number of samples or number of time duration where you have a channel fading, right? So if you specify, let's say, I want to make my Rayleigh fading channel like 10 seconds. Then when you make your simulator, you say, I want 10 seconds. Then all these things is done, and you get the output, which is a channel fading over 10 seconds. But that 10 seconds appear later when you do the same thing. Later, much later, I do it again. Okay, now I want fading of 10 seconds again. You get exactly the same thing. Okay, every time, because there's no random. So the Clark and Gans model, this is actually a papers, right? There are two papers one written by him, another written by this guy. So there are two papers, and put together we call this Clark and Gans model. In this model, they do it a little bit differently. What they do is that they start Gaussian. Okay, we have some Gaussian noise source. That means just Gaussian random variable. In MATLAB, for example, you can run rand_n function that will make a Gaussian random samples, Gaussian samples, right? So you have a Gaussian generator, Gaussian sample generator. You have another Gaussian sample generator, okay? And you generate as many samples you like for both of them. You multiply certain carrier frequency, cosine and sine, and then you add it, okay? Now the thing is that this is a random generator. Whenever you run it again, this will create the different random samples, okay? So there's a randomness here. You add it together. Why do you add it? Because that's complex. This is real, imaginary, okay? And then you get it. That's the Rayleigh fading. But before that, we put the Doppler filter. Why do we put the Doppler filter? What was a Doppler? Doppler, okay, we have a Doppler, right? As we learned earlier. So the reason that we put the Doppler filter is because that you want to make your random samples to be fluctuates based on your Doppler, okay? So without this, there's no fluctuation. I'm talking about the fluctuation like this one, right? The small scale fluctuation. You don't have fluctuation. You put the certain filter so that these samples now go through the fluctuation. Each sample follows a random, the Gaussian, right? Complex Gaussian. But the whole thing the amplitude now follows a fluctuation, okay? Based on the Doppler. So you need to design the Doppler filter. If you have a high Doppler, you design it based on that. Low Doppler, you design it based on low Doppler, okay? This is another plot. You can do it either this way or this way. It's basically the same. You can bring this one in here. Okay? Then you get this one. Either way is fine. So this is another plot that shows you a little bit details about this one. Okay? This one, this block here, same as this one. And Doppler filter here is this one. Okay? So basically the same thing. Okay, I captured this picture from one of the textbooks. So you can look at the wireless communication book. You will see this picture. Okay. Okay. So this is how you can create a Rayleigh fading channel. Looks pretty simple, right? Rand n is the function, MATLAB function. You can do this. This one you have to actually make it. There's a little bit effort here, but IFFT you can use a built-in MATLAB function. So everything looks simple, but in fact some of you already done this in homework, so you know that, right? It's not as simple as that. In fact, you do this, then you see some very weird output, right? So it's very good to do this one as practice. Okay, I want to encourage you to do this for fun. I'm not going to do homework now, but yeah, so it's better to do this practice. So here's the output. If you do that in MATLAB, then this is the output. So when you use the low Doppler frequency, like 50 Hertz, then you get this output. Okay, this fading profile. And if you use 200 Doppler frequency, then you will get much faster fluctuation, right? Fast Doppler. And one of the missing thing is that I didn't talk about anything about Doppler filter, right? So here's how you make the Doppler filter. So simply speaking, this is the equation. You can just develop this equation. You can just make a Doppler filter based on this equation. So this equation in mathematics looks like this. So we have a FC, which is carrier frequency, and FM is your Doppler. You should know your Doppler, okay? Whether you have 50 Hertz, 200 Hertz, you should know that. So FC, here's FC plus FM, that's the range, and your filter looks like this. Okay? Some bandpass filter. But this filter doesn't look like flat gain, but it has a very weird type of gain. Okay? And in fact, at this point, you have infinite. So, okay? So this is how you make your Doppler filter. And let's say when you have this input, let's say this is the input, this is just an example. Let's say this is the input in frequency domain, of course, and you put that into the Doppler filter, and this Doppler filter looks like this, then this is going to be your output, right? From this output, you can see that this filter basically suppresses some of the frequency, okay? It enhances some other frequency, and these other frequency which are enhanced are the frequency range in here, in the maximum Doppler, lowest Doppler. So now you understand why we are putting this Doppler frequency, because when Doppler happens, right, then you see that some of the frequency is shifted, and this frequency is shifted. So more energy is shifted on the boundary. Okay, that's why you see these kind of output when you go through the Doppler filter. Okay. Okay. The last slide, this slide basically shows you how to do simulation of the frequency selective fading. Earlier, this picture is the frequency flat fading. Okay? You have to keep remembering what exactly that means, frequency flat, frequency selective. So when you have a frequency selective fading, that basically means that within my symbol duration, I have a multiple path. Because my symbol duration is very small and your delay spread is very large, so you have to think about multiple symbols. Okay, multiple symbols. You have inter-symbol interference. My symbol is here, but my first symbol is affecting the second symbol. my first symbol is even affecting the third symbol, so there's an inter-symbol interference. Okay, because of those inter-symbol interference, you have a multiple of them. Okay, so you put here, right? This one is this one path is this one. So you have to create multiple of this. Okay, multiple of this, and then you multiply its own certain gain to add it together. That's how you extend the previous simulator into this way when the frequency selective fading happens. Okay, that's it for today. Any question?
Is there any, you see the deterministic path, there was a line of sight path for this Lysian fading.
In this case.
Really, okay.
Hmm?
Okay.
Okay, any other question? Okay, then see you next week.